Great. Thank you, Dongwook. And thanks for the organizers for the invitation to this super interesting conference. And I was going to talk about two different topics here today. So the first one is regarding molybdenum disulfide. And we heard yesterday that this is a material that exhibits orbital Hall effect. And I want to describe another response this material has in which when you apply an electric field, you induce a change in the charge density distribution. And I want to show that this change in density distribution can be related to the orbital Hall conductivity. And then I'm going to talk about a different system, twisted double bilayer graphene. And in this case, we'll look at in a non-ordered state. So this is not a spontaneously symmetry broken state. So in a non-ordered state, how does an applied magnetic field change the energy spectrum, which is related to the orbital magnetism? So these are both rather distinct systems, but in both cases, we have non-magnetic systems with valley contrasting Berry curvature, and we're finding ways to measure this Berry curvature. So let's start with MOS2. So as we learned, MOS2 has a orbital or valley Hall effect, and that can be understood in terms of an electric field-induced change in the wave function velocity, or the anomalous velocity. And what I'll show is a new relationship which relates the wave function velocity to a wave function charge density distribution that applies for this material. And we can combine these two things and therefore understand the orbital Hall effect as not a change in the velocity, but instead a change in the charge density distribution. And this is something that's in principle measurable, so you can measure this to get that. So here's the electronic structure of molybdenum disulfide. The valence and conduction band extrema are dominated by d orbitals on the molybdenum atoms. And for example, at the valence band at the plus k and minus k, or k prime points, these orbitals have atomic orbital angular momentum of plus and minus 2 at k and minus k. And so, as we learned yesterday, if we look at the minus k valley, we have an orbital angular momentum of a state. And when I apply an electric field, say upwards, the anomalous velocity will push this state towards the left. Similarly, at the plus k valley, we have an orbital angular momentum pointing in the opposite direction, so the anomalous velocity changes sign. But you end up with a transverse flow of orbital angular momentum. So that's the orbital Hall effect. Note, I'm not going to invoke any spin in this talk, so we're just going to ignore the spin degree of freedom. So, so you can understand this anomalous velocity in terms of the Berry curvature. And indeed, you can define the Berry curvature as the tendency for a state to, when pushed with an electric field, develop a velocity that's transverse to the electric field. So this omega here is what I denote the Berry curvature. The total Berry curvature of a material gives the intrinsic anomalous Hall effect, or conductivity. In this material, it's non-magnetic, and so these two Berry curvatures from the opposite valleys cancel each other. But when you look at the orbital Berry curvature, if you like, or the orbital flow, then you get something that's not equal 0, because the orbital changes sign between the two valleys. So here is a result we derived in this paper here a couple years ago. And the question is, what's the velocity of a block wave function? And so let me make some assumptions. So first of all, I'm going to assume that we have a monoatomic unit cell with orbitals of the same character. So only s, or only p, or only d. And we only consider sigma hopping. So we ignore pi and delta hopping. And let's say here's our block wave vector pointing off in this direction. And we show that the velocity of a state is given by this expression here. So it's a sum over neighbors. This T sub Ri, that's the sigma hopping between our primary unit cell and the ith neighbor. And this is depends only on the distance between the two atoms. Here Ri, so that the bond current is directed along the vector connecting the two sites. This factor here says that the block wave vector and the displacement between the two sites have to be have some overlap. And finally, we get this angular dependence of the charge density. And so, for example, if we had a charge density which looked like this, the wave function wouldn't be along the block wave vector, but would be preferably along this horizontal direction. And so I won't go into the details of this derivation, but just to mention, if you're curious, what we ended up doing is normally this hopping parameter here depends on the relative orientation or displacement of the two atoms. And we exchanged the angular dependence for this hopping and sort of transferred it to the angular dependence of the wave function density. And I have to stress, you can only do that with these assumptions here. And so if you have a material that doesn't satisfy these assumptions, this doesn't work at all. So it's kind of like a very restrictive relationship. Okay, so this was our buried curvature picture. We said when we apply electric field, we change the velocity. Okay, well, the velocity is related to the charge density, and so therefore you must change the charge density. And then we'll show that we can relate that to the orbital Hall conductivity. So here's the cartoon of how this works. So here's a ground state wave function at the capital K valley, the band extremum. So the velocity vanishes there. Here's the block wave vector there. And it turns out the charge density of the ground state is isotropic. And so if you use the formula I had a couple slides ago, you can convince yourself that the bond currents between these three bonds all cancel each other. There's no preferred direction. So the velocity is 0 there. Now, when I apply an electric field in the positive y direction, what happens, as we'll show, is that the charge distribution gets modified. So there's less charge along the x-axis, and there's more charge along the y-axis. And that breaks the symmetry of the bond currents, and so you end up developing a velocity going to the left. So that's the cartoon version of this. We can also calculate this change in velocity per electric field with DFT. So this is using quantum espresso, Wannier 90, and getting out the real space orbitals from Wannier 90 and do linear response and see what is the change of the total charge density when I apply an electric field. And it looks like the cartoon I showed you before. And we can make some more specific relationships if we consider a two-band model of this TMD. So this is the two bands are the conduction and valence, and here are the real space orbitals corresponding to those two bands. So those are defined in real space. And you can analytically compute the linear response, the change in density you get from this model here. And you can also compute analytically the orbital Hall effect. And I have some relationships here that are derived from that procedure. And what's important is everything on the left-hand side of this equation here depends only on the charge density response. There is one free parameter, T, the hopping, but you could get that if you knew the effective mass. So if you gave me a measurement like this, I could compute the left-hand side based on your measurement. And I skipped some of the details here. This x-min has to do with the distance between the atom and the minimum of the change in density. But suffice to say, it only depends on the charge density response. And you find that that is equal to the computed Valley-Hall conductivity for this model. And you can also make a similar relationship for the energy resolved orbital Hall conductivity. Yeah, I forgot to mention, this is for the insulating state here. So you can also do this energy resolved and get a similar kind of relationship. So we can compute these two things with DFT independently, left-hand side and right-hand side. And so the left-hand side, I just use the real space picture I showed you, and I get a value of 0.95 over 2 pi. And for the right-hand side, I get a value of 1.05. So they're semi-quantitatively similar to each other. And similarly here, I'm doing the energy resolved conductivity. So this red curve is just from the change in the energy resolved real space density. And I have Valley-Hall and orbital Hall conductivity plotted. Let's take a look at orbital Hall conductivity. It's a black dotted curve, and you see that there's decent agreement, I would say semi-quantitative agreement between the two ways of calculating this quantity. So since we have the DFT results, we have a notion of how strong this effect is. And if you assume that MOS2 can withstand a certain amount of electric field, you can ask, is this measurable or not? And so our estimates is that you would need a probe of the real space density with sub-angstrom spatial resolution with sensitivity of a part in 10 to the minus 4. So here is like some examples of high resolution real space imaging. As to whether or not this is experimentally feasible, I'm honestly not really sure. As I look at it, I'm not an experimentalist. It doesn't seem obviously impossible, but I don't really know. But these are the requirements anyway that you would need. So that's the first part of the talk. And so the idea was that you can, in principle, measure this charge density distribution, and it tells you something about the orbital Hall effect. Measurements difficult but feasible. Open question, is this velocity density distribution formula that I showed you before useful in other contexts? So it's something I spent time thinking about, and yeah, so far the answer has been no. So I'm not sure if this is sort of an observation that's only useful for this particular material. I think that remains to be seen, but I'm happy to talk about what I've tried and what hasn't worked with those who might be interested. Okay. So now I'm going to switch gears and talk about a different system, twisted double bilayer graphene. So this is a little bit different from the other types of systems we've heard about in the conference, so I'll give a little bit of background. So let's start with twisted bilayer graphene. And I'm sure you've heard all the interest in this material system, that it has flat bands and interactions are very important. One thing you can do is ask, why are the bands flat? And so let's start with a Bernal stacked graphene bilayer and suppose that the layers are uncoupled from each other. And so I have a linear dispersion at the K and K prime points. And I'm going to rotate the top layer with respect to the bottom. And you see these moire patterns starting to emerge. And what that does is to displace the Dirac cone of the top layer relative to the bottom by an amount which is related to the twist angle, like this. And now when I turn on the coupling between the layers, this band crossing here will open up a gap. Let's say that's, so that the value of energy of that band crossing is given here. It opens up a gap of, say, 2W. And you can imagine trying to tune the system so that this lower state gets pushed down in energy to the 0 energy level. And so this could be the condition for a flat band. And if you plug in the well-known parameters for graphene into this estimate, you get an estimate for the magic angle of 1.5 degrees, which actually isn't that far off. It's in the ballpark. So this is the band structure from the original paper from Bistritzer and McDonald. And you see that at this magic angle, the bands turn out to be flat in pretty much the entire Brillouin zone. And of course, that's interesting because these small bandwidths mean interactions are important, so you get strongly correlated physics and stuff like that. So let me just show you this in reciprocal space. Here is the Brillouin zone of the graphene monolayer. There's our K and K prime valleys. And then the top layer is twisted a little bit. And these mini Brillouin zones form due to the coupling between the layers. And all the action occurs inside this mini Brillouin zone. So the real space unit cell is really big, so the reciprocal space unit cell is really small. Okay. So this is like a very small subset of the many references out there on this on these types of systems. So there's a whole different family of different twisted bilayer, trilayer, quad layer graphene structures with different twist angle configurations and all sorts of interesting things like unconventional superconductivity have been seen. You can also get these moire systems by just stacking two different TMDs on top of each other, and the lattice mismatch is sufficient to give you this long wavelength moire pattern. And here's a reference in which they show that such a system shows magnetic order. So that's seen by looking at the Hall conductivity in zero field and observing hysteresis. And then here's a recent preprint in which they showed that applying a current to such a system can modify or change the magnetic order, leading to dynamics. Okay, so the flavor of graphene that we're interested in is twisted double bilayer. So we have two Bernal stacked bilayer graphene layers, and we put them on top of each other and put a twist angle in between them. The angle we look at is kind of far away from the magic angle. It's 1.8 degrees. We chose that because it was sort of a less explored region so far in the literature. And so actually, like, interaction effects and stuff like that are not important for what I'm talking about. This is all like single particle physics. So there's an important symmetry for this system. There's twofold rotation about the y-axis of the pristine crystal. And that implies that the total Berry curvature in the K and K prime valleys has to vanish. But when you apply a vertical displacement field, you break that symmetry. And then the K and K prime valleys can have a non-zero Berry curvature. Now again, it's non-magnetic, so it's equal and opposite Berry curvature on the K and K prime valleys. And here's just a small sampling of references that have done experiments with this twisted double bilayer. Okay, so this displacement field is a really important knob, and let me show you the band structure of the capital K valley for different displacement fields. So first of all, you notice that the conduction and valence band are kind of separated from the other bands. The bands aren't like that flat here, as I mentioned. The color coding is the Berry curvature in units of nanometers squared. And on the bottom, I'm showing the Berry curvature in the entire mini Brillouin zone of the capital K valley. And you see that there are hot spots when the bands get close to each other. Now, as I increase this displacement field, there'll be a band crossing at the lowercase k point, and then the bands will reopen again. And so you can see as these bands get closer and closer, the Berry curvature gets super high as they're approaching each other. Band reopens. It turns out that the valence band will then have a Chern number of -2. And you see that this complex distribution of Berry curvature. Okay, so this is for the capital K valley. Let's see, there it is. There it was. And then for the K prime, it's equal and opposite, like that. And so this, the strong Berry curvature indicates that likely you have orbital magnetism. And so what we have is a system with a plus orbital magnetism at plus K and minus orbital magnetism at minus K. And we'd like to find a way to measure that valley-resolved orbital magnetism. So one way to do it is just to apply a magnetic field. So a magnetic field will couple to these two orbital moments in the opposite sense and then split their energy level like that. And all you have to do is measure the change in energy level versus magnetic field and get like the G factor. And that'll tell you something about the valley-resolved orbital moment. So to do this measurement, you need a magnetic field. You need a displacement field to induce this orbital moment. You need to be able to do spectroscopy to get these energy levels. And it has to be low temperature because these are narrow bands. And so the energy splittings are pretty small. So, so at NIST, my colleague has been doing this measurement using scanning tunneling microscopy for Landa level analysis. And so what they have is an STM with a backgate. It's at low temperature. So the backgate allows you to change a displacement field. So we have that knob. They can apply a magnetic field to 15 Tesla. And then you can vary the tip bias to get the energy resolved density of states. So like on this axis here, we're changing the displacement field. On this axis, we're varying the bias. And so we're getting the energy resolved density of states. And then the color coding is the density of states. So this is that valence band. This is the conduction band. And you see all these like lines here? Those are Landa levels. I'll talk about those in a second. And what we're interested in is something like this, where we fix the displacement field and we vary the magnetic field in this direction. And then we're looking at the energy levels along this axis here. And you see, okay, Landa levels are splitting, they're moving, and stuff like that. We want to analyze that to figure out this valley-resolved orbital magnetism. Okay, so let me actually kind of just discuss the basics of these Landa levels. So what we do is we apply a strong magnetic field out of plane, and that will induce cyclotron motion of the electrons. And if the electrons complete a orbit before they scatter, then the spectrum collapses into discrete Landa levels like that. And the size of the orbit is related to this magnetic length, just inverse to the magnetic field. And so if you want to know the degeneracy of a Landa level, okay, it's just how many such orbits can you fit into your sample. So it goes something like this. So they have macroscopic degeneracy. And so the question is, okay, what determines the energy levels of these Landa levels, the energy values? And the easiest way to understand that is through this Bohr-Sommerfeld quantization rule, semi-classical. And all it says is that, okay, we have electrons moving around in circles. And so what we need is that as they do that, their phase will accumulate. And we need that the total phase accumulation is an integer multiple of 2 pi, kind of like the quantization rule for atoms. So, so there's the phase accumulation as the electron goes around the orbit. Now, it turns out you can show that this is equal to the area in K space traced out by the cyclotron orbit at constant energy E. So that's what this is here. I'll explain this more in the next slide. And multiply that by LB squared, that has to be 2 pi n. So all this is saying is that the orbits have a phase change of 2 pi when they go around. Okay, so here's our like AK of E versus E. So this is the area of the zero field Fermi surface, if you will. So we're in 2D, so as the energy is small, our Fermi circle is small, and then it's getting bigger, bigger, bigger as we increase the energy. And then we reach the middle of the band, and now it's getting smaller and smaller, smaller. Okay, and this quantization rule says that this area has to be an integer times this factor here. So an integer times this thing for n equals 0, 1, 2. And the place where those two things are equal, these are the allowed energies. So that's where the Landa level energies come from. There's an extra term here, Maslov phase. We don't need to worry about that. But it's not the total story because we might have an orbital moment of these states. And when we apply a magnetic field, you change the energy level because of the coupling between the orbital moment and the magnetic field. So the energy levels should be shifting because of that coupling. And so if we assume, for example, that the orbital moment is just constant throughout the entire energy range, all the energies would get shifted a little bit because of this coupling. And so the energy levels wouldn't be where those dashed blue lines are, but where the green lines are. And so you need to include that correction. And so that has to do with the average orbital moment at a given energy. So it's given by this expression here. So this is our orbital magnetization. Here, E is sort of like a Fermi level. And we need to take a derivative with respect to E to get the energy resolved. And at the end of the day, you end up with a modified Bohr-Sommerfeld rule, which includes the orbital magnetization. So this factor here is dimensionless and just given by this integral. Okay. So let me show you some calculation results first. So there's a lot of stuff on this slide. This is actually my second to last slide. So I'll take my time with this one. So here's the magnetic field along this axis, increasing it. Here's the energy, and I'm plotting what the Landa level energies are. And there's two colors. One is red for the K valley. The other is black for the K prime valley. And you see that these two levels are, these two valley energy levels are splitting, and that's due to this orbital magnetization. These solid lines are from the semi-classical approximation I just described to you. And I also include dots from a quantum calculation of the Hofstadter spectrum. So you can see that for many of the energy levels, the quantum and the semi-classical agree pretty well, although not for all energy levels, which is kind of interesting in its own right. So let's take a look at some of these levels here. So this is, again, the bottom of the valence band. This is a 0th Landa level, and I see the splitting there. And so that's what we kind of want to be probing experimentally. What's interesting, when you go to the top of the valence band, the splitting is actually huge. So there's the first black line right there. There's the second black line. But now there's the first red line. So the inter-valley splitting is actually greater than the Landa level splitting because the G factor up here is so big. It's about 40 at this part of the band structure. So if you try to analyze the experimental spectrum up here, it's going to get super confusing because you don't know what's the valley splitting and what's the Landa level splitting. So it's better to be down here where a single Landa level is far away from all the others, and you can see the splitting there. Okay, so what I plotted here is, here's the valence band energy, and then the color code is the Berry curvature. And these are the iso energy contours. So, you know, this quantization condition has to do with the area of the contours. And then this correction due to the orbital moment has to do with the amount of Berry curvature that's enclosed by the contours. And we see that because the Berry curvature is very large near the top of the valence band, you get a huge orbital moment there. And it gets smaller when you get to the bottom of the valence band. Okay, so I'm just going to show like very small amount of experimental data. We have a lot of data, but it's still very active analysis going on. So evidence for value splitting of 0th Landau level of valence band, you know, question mark. So here is the experiment for 0 displacement field. Again, we're looking at the valence band and kind of focusing on the 0th Landau level. There it is. Okay, it's moving in energy because of this like Bohr-Sommerfeld rule. And here's the theory. So here I'm just looking at the top layer density of states so that we can compare with the STM. And okay, the theory, there's definitely no splitting, right? And in the experiment, I don't know. Maybe there's no splitting. It's not obvious to me that there is. When we turn on the displacement field so that we expect to see valley contrasting orbital moment, it appears as if there is some kind of splitting in the 0th Landau level. And of course, the theory shows that splitting too. But again, this is like kind of early analysis, I would say. So basically, the takeaway there is Landau level spectroscopy can measure valley orbital magnetism splitting when it's not too big so that it doesn't get mixed up with Landau level splitting. Okay, so with that I'm done. Thanks to collaborators. So some postdocs worked with me, Fei Zhui and Vivek Amin, on the first part of the talk with the molybdenum disulfide. And then the experimental group at NIST has done all the work on the twisted double bilayer graphene. So yeah, we kind of like went through a lot of stuff, but I would say there's some unifying notion that we're trying to find measurements that tell us something about valley contrasting Berry curvature in non-magnetic materials.